So I'd like to say hello and welcome to this mini workshop that will be held by me, Maria, and my colleague Ruben. And it's lovely to see you. And it's lovely to see you, so many of you being able to attend. And the agenda for today is to start with a presentation. And I thought we could save the questions for last, but please don't hesitate to ask if there is anything that is unclear. And then we will continue with a discussion on how artificial intelligence and machine learning can be applied in your domains. Okay. Next slide. Yeah. So who are we? Maria, Erman, and Ruben Cubo. And our background and expertise are in signal processing, telecommunications, machine learning, and artificial intelligence. And we also have a few other people involved in our work package. And it's Thomas Gustafsson, and who is the work package leader. And then we also have 3 master thesis students that have been working with us for the past few months. And me and Ruben are situated in Uppsala, Sweden. And we are part of AFRY, and it was previously known as ÅF Pöyry. And it was founded in 1895 in Sweden, and it currently has offices around the world and approximately 17,000 employees. And next slide. Yes, our work package is called Climate Action, Making Data Widely Available. And these are tasks and deliverables. And the first one is a pre-study on inquiries and needs from research stations to identify data sets and questions to be answered. And our hope is for this workshop to lay the foundation for this specific deliverable, and hence your feedback and ideas would be very useful to us. And we would also very much appreciate to get in contact with you for further discussions. Other tasks and deliverables are exploring possible applications of machine learning, focusing on topics related to land use, isescapes, landscapes, and ecosystems, using machine learning on example data to make specific algorithms and methods available and demonstrate the outcome, increase awareness of machine learning and artificial intelligence and how to use that technology. Next slide. Okay, so let's go on to a hopefully gentle introduction to AI. Yeah, so what is artificial intelligence? Basically, it's not a new concept, and you can say it's a branch of computer science that aims to make computers act and think like humans. And if the desired outcome is to approximate human-like, then what is needed? First off, we have data, and usually we need a lot of data to get a good result. So for instance, with an artificial neural networks, which we'll talk about later, we might need perhaps thousands of images to train a network. Or in the case of text, we might need something of the equivalent of thousands of books of text. Also, processing power is very important. Again, with the example of an artificial neural network, it might take hours to train a simple network, even with a powerful home computer, and even a simple network. And that's why often cloud computing services have become so widely used lately in the areas of machine learning and artificial intelligence. And why is AI of interest? Well, basically, the amount of data generated far exceeds humans' ability to absorb, make decisions based on, and interpret that data. And complex decision-making is based on patterns, and it's not really feasible for humans to process and find patterns in such huge amount of data. Okay, as I said, with regards to AI, it's not a new concept. You can say that AI was intimated in Tin Man, Who Lacks a Heart in The Wizard of Oz. which is from the beginning of the 20th century. And not to mention the human robot impersonating Maria in Metropolis. And by the 50s, a generation of scientists, philosophers, and mathematicians are occupied with AI. For instance, Alan Turing devises the Turing test, arguing that a thinking machine is plausible. And checkers and chess programs are already created in the 50s that challenge amateurs. And this all culminates with a historic conference in 1956 in Dartmouth, bringing together leading scientists, laying the foundation for AI as we know it. And in addition, these same scientists continue to be very influential in AI in the following decades. Yes, a history of AI continuing this, and even advanced AI techniques, such as neural networks, were introduced as early as the 1950s, but because of limited computational power and memory, its breakthrough was prevented. And a primitive example of another branch of AI, natural language processing, or NLP, which we'll talk about later, was ELIZA. And this basically simulated conversations. And in 1997, Deep Blue gained a lot of attention when it defeated the then reigning world champion Garry Kasparov in chess. And in 2016, Google's AlphaGo defeated South Korea's Lee Sedol in Go, a game vastly more complicated than chess. And as part of one of AlphaGo's victories, there was one very unconventional move that surprised even like the masters of the game. A history of AI in popular culture. Well, AI has been a recurrent theme in cyberpunk, dystopian, apocalyptic science fiction, basically the rise of a machine, which we are quite familiar with. Some notable examples, we have like H.G. Wells and his warnings of dangers of powerful technology in the hands of humans. We have Mary Shelley's Frankenstein, and we have Isaac Asimov and his supercomputer Multivac. We have Arthur C. Clarke, notably the Stanley Kubrick directed 2001, A Space Odyssey, with its HAL, which is a sentient computer. And of course, we have the excellent Japanese anime Ghost in the Shell, and which later went on to inspire the whole Matrix franchise.
All right, so now it's my turn. So thank you for the nice introduction to the history of AI, Maria. So how is AI applied in life? And the good thing about the life is that there are a lot of patterns that can be learned by artificial intelligence. But here is the thing, AI systems can only focus on one pattern at a time. So they are very narrow on scope. For example, if you train an AI system to identify animals, if you put the system into identifying humans, then it's not going to work properly. And it also can be relatively easy to fool. You can see an example on the right side where you have a panda, for example. Then you put some noise in the image, and then it identifies the panda as a gibbon. And for a human, you can say, but what is the difference? It's a panda still. But sometimes the computer doesn't classify properly. There are some other examples, like for example, if you rotate a vulture picture, the AI program can say, it's an orangutan. It doesn't make any sense for a human, right? And as Maria mentioned before, another shortcoming is that they need a lot of data to learn something, which in some disciplines is okay, there is plenty of data around, but in others, such as, for example, satellite imaging, is a challenge because there is not enough data to go around. And if you try using AI to predict something that is random, with no underlying pattern, then it's completely useless. One sec, this is done. There we go. So as Maria mentioned, AI has been around for many decades, but why is it important now? Why all the hype? And one big thing that happened recently is this transition from being fed the patterns. So for example, if you have an expert telling the computer, okay, if you see this, do that. That's how it was done, for example, with ELIZA. But nowadays, the computers themselves learn those patterns. But learning the patterns is not that useful. What you want to do is to make predictions using new data that has the same pattern and then predict something. As Maria mentioned, when AlphaGo beat Lee et al. Back in 2016, it used a move that not even the grandmasters, people who have played Go for many years, will have done. So one of the good things about AI is that it reveals information hidden in the data. And other examples can be unknown patterns in nature related to climate change, biomarkers not considered by doctors, for example, for cancer detection, and there is a lot of examples around. And one of the biggest drives is that there is a lot of money involved. So lots of companies are investing a lot of money into these systems. So for example, in task automation, think self-driving cars, think industrial robots, think, for example, this Roomba robot that uses AI to orient itself in the house and so on. Marketing, so personalized advertising is a very big field. Increase efficiency and productivity. So for example, things like preventive maintenance. So try to see the pattern of the life cycle of some very complex machine, predict when it's going to need maintenance and get everything ready. So you lower costs that way. And nowadays, AI and machine learning are very close together. You cannot say one without the other. And machine learning is not really the new kid in the block. It's nothing new. And some people think that it's a fancy name for just using statistics to learn patterns in the data. And most of the algorithms that are used nowadays have been around for a very long time. So I guess some of you at least have used linear regression at some point in their lives, in your lives. And that's the most basic machine learning algorithm. So if you have used linear regression, you have used machine learning. Then there are some other algorithms, like for example, K-means clustering has been around for more than 50, 60 years. Principal component analysis for dimensionality reduction. I will explain a bit more later about those algorithms. This has been around for more than a century. The perceptron, that is like the precursor of neural networks and deep learning 60 years ago. Neural networks themselves were formalized already in the 1980s, and first deep learning ideas were already in 1967. So nothing new. However, this has boomed tremendously in the last 10 years or so because we have much better computers and a lot of data to feed them. So that's why it's quite hot. And I'm going to show you a video. Let's see if I can say like this. About a couple of projects that we have done at A3. Can you see the video?
We can.
Yes, we can.
Okay. So this first video is about an app called Flowety, and now with the coronavirus, social distancing is a pretty hot topic. So with this, you feed video, and it detects whether the people in the picture are doing social distancing correctly or not. As you can see on the upper left, some green dots when they are distancing properly and red dots when they are not. As you can see the original image on the upper right corner. So quite cool stuff and very relevant now with the coronavirus crisis. And the second one is perhaps more of interest of you guys, is geology pattern recognition. So trying to find faults in rocks. maybe determine hazards for landslides and so on. And this is a group that has done this in Austria. All right, let me set this back up. Okay, so another important topic when it comes to artificial intelligence is ethics. Paraphrasing a quote from Jurassic Park, just because you can do something doesn't mean that you should do it. Fortunately, an AI like, for example, Skynet or HAL 9000 is not possible with today's techniques, although some people think that in 30, 50 years it might be possible. One more current topic is explainable AI. So lots of algorithms are quite complex to interpret, and quite often they are just black boxes. And to make things worse, some methods are kind of the lifeblood of some companies. Think, for example, how Google do their search algorithm. That's proprietary information, and they get a lot of money out of it. There are also some dangers that are associated with AI and societies, things like unemployment, although this is a controversial topic. Discrimination due to biased data. So some algorithms have discriminated against, for example, blacks in the US. Things like privacy. So in the European Union, there was this GDPR that is trying to protect personal data. Or in the medical realm in the United States with the HIPAA regulation. And also getting illegal information from legal proxy data. So it's possible to get data for example, fitness trackers or smartwatches to build a medical profile. And those data are completely legal to take, and one can build these kind of profiles legally. And they are, let's say that those medical data is confidential for a reason. There's a lot of trouble there. Something to keep in mind. Now, machine learning can be used to solve a lot of problems. I will give you a very quick flavor of what can be done. I mean, if one could go in length for every one of these problems, we can be here for months. We only have 40 minutes. And this is kind of a 10,000 feet view of the machine learning world, or at least part of it. You can see 4 big groups: classification, regression, clustering, and dimensionality reduction. And you can see here that there is a lot of options. So yeah, huge world. And I will try and describe it in like 10 minutes. So the first problem is regression. So by definition is predicting a continuous unordered quantity from input data. Some algorithms that are used for regression are linear regression. It's causing non-linear regression. So instead of fitting to a line, you can fit to a polynomial, you can fit to an exponential. Regularized regression, just in case you have noisy data or you want to do some sparsity on your features and so on. And use cases where this can be useful. So, for example, the temperature increases from CO2 emissions, relating weight and height of a person. You can see an example in the lower right corner. You can see lots of data points of weight and height. And there is a kind of a linear trend pictured by the red line over there. Predicting housing prices for both local and house characteristics. And predict how much the stock market will be in some time, say tomorrow or in a week or in a month. The second kind of problem is classification. And in classification, you want to predict a non-discrete or non-ordered characteristic from data. And kind of the archetypical example is to classifying cats from images. So you can see an example there on the right. You give the computer an image with a cat, and the computer should say, this is a cat. more intricate algorithms, you can feed an image with several animals, like 2 cats, a dog, and a duck, for example, and the computer can tell you that there are cats, there's a dog, and there is a duck. Some examples of algorithms that can be used: logistic regression, support vector machines, and decision trees. And some other use cases apart from classifying animals is, for example, segment environment for self-driving cars. You can see an example on the lower right of the screen, where you can see there that the road is painted in purple, people in green, some posts and signs in yellow, and other cars in orange. Some other use cases: vegetation composition from satellite imaging, so things like the color of the vegetation, humidity, and so on can be of use. Character recognition, so if you write something on your envelope, like on an envelope, like an address, a machine can recognize that address from your handwriting. And back to the stock market, you can also predict whether the market is going to go up, in which case you buy, or if it's going to go down, in which case you sell. The third kind of problem is clustering. So let's say that you have to get lots of data without labeling, and you want to see which data are close to each other, given some characteristics. So for example, think music genres, or think recommender systems, like you are this age, you have bought this stuff during last year, and let's put you together with people of similar tastes. Things like that. The good thing is that there is no need for labels, so usually getting the labels is a very time-consuming endeavor. Some examples of this: k-means and spectral clustering. And some other use cases, apart from the examples I just mentioned, is, for example, word clustering, so inferring synonyms from words. Sorting of Arctic clouds, you can see an example on the upper right corner. And grouping of aerosol sources regarding pollution. The last one is dimensionality reduction. So let's say that you have a data point that has a lot of dimensions, but that's very cumbersome. Maybe not all the dimensions are relevant. Some of them might be combinations of other dimensions. That can be the case. So one could project that data point in a very high dimensional space into a lower dimensional space. You can see an example on the upper right. So you have a 3D cloud of points. And you cannot see much about it, but if you project it in the right way, you can see a clear division between 3 groups, one here and one here and one here. You cannot see that in this image. So yeah, dimensionality reduction is in a nutshell a projection. Another example is image compression here. So you have an image, and depending on how much you compress it, you can see here that this image and this one is pretty much useless. You can see here in the third image that you can see the face, but it's still quite choppy. But as you increase the dimensions, for example, in 30 or 40 dimensions, you can see that it's pretty nice quality, and the image size will be greatly reduced. Some examples of algorithms that are used for dimensionality reduction: independent component analysis, principal component analysis, and singular value decomposition. And you cannot have an AI talk nowadays without deep learning. So deep learning is not a new concept. The first ideas were already in '67. And the idea behind deep learning is to approximate complex nonlinear relations, data features, and hopefully learning those relations in an automated way. To pay the price, because these models are quite complex, you pay the price by requiring a high computational power. And until recently, this was not possible. But and even nowadays, you need specialized hardware like GPUs or hardware specially designed to do this in order to find those relations. And there are several variants of this. So the building block of this is the neural network. And you can have a fully connected network of neurons. So in this picture, each dot is one neuron. And you can see here that everyone is connected to everyone. That's a possibility. It's called a fully connected neural network. There are some other more smart transformations that one can use. Those are quite recent, actually. For example, one can use the information of neighboring features and see how are they related instead of doing it feature by feature. And then you get a convolutional neural network that is very used in image processing nowadays. And the fundament is very simple. So you feed it an image, and then by seeing how the neighboring pixels are related, it can detect, for example, things like edges, circles here. Then from there, you can build combinations of those to detect, for example, you can see some small wheels here, a door, and so on. You can go further and have some kind of proto cars here at this height. And at the end of the day, you combine them and say, okay, this is an Audi A7. That's how this works in a nutshell. Another possibility is to feed it a sequence of data and see relations with the past. That's what they use in a recurrent neural network. And there are many others. This is a booming field, and there has been a lot of different options coming up in the last 5-10 years. Very hot topic. Now, when you train your model, you have a very nice predictive power, blah, blah, blah. You get a metric, usually some variation of accuracy, but something that is important is that on their own, they don't say much. Take, for example, a clinical trial of a drug that is 97% effective in a random population. But if the disease that you are trying to cure is only prevalent in 1% of the population, then you are doing worse, even though 97% on its own is pretty nice to see. So one cannot take a metric on its own. It has to be in a context and against a baseline. And also sometimes even very nice accuracy numbers are completely useless. Think, for example, a self-driving car with 99% accuracy. That means that 1 in 100 actions is going to be wrong. And I don't know about you guys, but I wouldn't drive a car. I wouldn't ride in a car that is has that kind of reliability. One can also use graphical visualizations, such as confusion matrices. You can see an example over here. So you have a doctor telling someone that is pregnant or not. And you can see that in the diagonal here, those two cases are true positive and true negative, so they are correct. But it can happen that you tell a guy that he's pregnant, or you can tell a visibly pregnant woman that is not pregnant, and that's a mistake. And that is much more interesting to see than just an accuracy measure. Of course, plotting, training accuracy plots, so how the algorithm is performing as it trains, time series. Interactive dashboards, you can see an example here of, this is a deep learning setup. And the computer is trying to learn a pattern, and this is quite cool. This is an interactive dashboard. It's called TensorFlow Playground. If you have the time, I recommend that you look at it. It's very intuitive, and you can play with different parameters. And we can also use new technologies such as virtual reality, augmented reality, and so on. For in some cases, they might be useful. All right, so I will give the word to Maria now.
Okay, thank you very much, Ruben. Yeah, let's go into interesting application areas. So we have a discipline from AI that's called natural language processing. That's also gained a lot of attention. And it's a way to analyze language data. And one way is with speech recognition, determining the textual representation from the audio of a person's voice. So for instance, we can use, if you have an iPhone, Siri, or Google Assistant, or Alexa, if you want to dictate. We also have text-to-speech. Basically, you have a computerized voice that reads text for you. And machine translation, where we can have this textual representation and have this automatically translated from one human language to another. And we have sentiment analysis, extract meaning from blocks of text. And from this meaning, we can, for instance, build a recommender system that recommends blocks of texts with a similar meaning to each other. And we also have the chatbot, which is a conversation simulator. And maybe you have come across that when you go to a website and you want to ask for help, and then you will get like computerized answers depending on what questions you pose. Optical character recognition, OCR. This is a classical machine learning technique pertaining to natural language processing. And this is a way to convert images of text that can either be handwritten or typed into computerized text, which then can be further processed. So basically, as you can see on the right, we have trained a neural network with different variations of letters and by using a software MATLAB. And then we feed it some inputs, and then we can see the results from a neural network. And even when we feed it heavily distorted digits, it kind of brings out quite reasonable output numbers. And a typical use case of OCR would be, for instance, if you is in a restaurant and you photograph a menu in a foreign language, and perhaps you want to photograph a traffic sign, and then you will have the text recognized, and then you can further process this by, for instance, translate the foreign text into your own language. That's a typical use case. And as I said previously, the procedure for character recognition is, for instance, train a neural network to learn variations of letters, and then you do pattern recognitions from these letters. Internet of Things. This is very much a current concept and also a bit of a buzzword, but we still think it might be of interest to the Interact community, and that's why we have added it to our presentation. So basically, anything that can be connected will be connected. So anything connected to the internet, but commonly used to denote devices provided with unique identifiers that talk to each other. So it's a concept of devices, networks, and data, where each device collects data for a specific purpose. And a common use case is smart home products. And of course, there will always be some drawbacks, and the obvious ones are security issues and privacy, and also incompatible standards. But the benefits are that you can access information from anywhere at any time on any device, and you can also automate tasks. And this can be like very useful for instance, remote sensing. And finally, we have some ready-made AI solutions. There's no need to develop everything from scratch. And as most of us know, I guess, we have the virtual assistants like Siri, Alexa, Cortana, and Google Assistants. They help us dictate, they help us answer questions, they make recommendations based on those questions and they perform actions. For instance, they start programs. You can have like your headset in your car and ask Siri to play music, read emails, anything. So those are ready-made AI solutions. We also have a few, quite many actually, but it's worth mentioning Amazon Recognition, for instance. It's a video and image analysis and classification service. We have Amazon Poly that converts text to lifelike speech. And we have Amazon Deep Lens, which is a deep learning enabled video camera, and it pretty much gives you machine learning with a fully programmable video camera. And apart from mentioning a few Amazon Web Services, which are perhaps the most used and most famous ones, we also have upcoming, or yeah, not upcoming, but other famous that are starting to take more market share, and those are Azure and also Google Cloud. Okay, so thank you very much for your attention.